Anyway, welcome everybody. So this is Can LLMs Plan course overview. So first, just a little bit of what this is. So Gridspace, if you're not familiar, we're a speech and language technology company focused on machine learning for long-form conversational speech and language. If you are joining from MIT, you already know what IAP is, but if you're watching on YouTube or somehow are watching somewhere else, IAP is a short month-long scholastic period in MIT where you can learn about things that you wouldn't normally be able to learn about in a school setting. And so we do these lectures to try to teach more about speech and language technology. Last year, we did kind of a broad overview about speech, language, signal processing, NLP, linguistics. This year is going to be focused on things that LLMs can't do. Does anyone on the stream want to say hi or introduce themselves? You don't have to. I'll take that as no. Okay, well, at the end, if you guys have questions, you can either post them in the chat or just at any time speak up if you're on the stream. If you're on YouTube Live, we'll try to monitor for comments there as well. So if you want to learn more about Gridspace, or if you guys aren't yet that familiar with us, you can start by going to gridspace.com or go to our YouTube, where we have a large amount of content about speech, language technology, about bots. So this is where we're headed in this year's IAP course. So three things. One, what are the limitations of large language models? So what are things that a language model or a large language model by itself struggles to do in the broad spectrum of cognitive tasks that either other computer algorithms can do or that the human brain can do? So we're also going to talk about how you can then augment large language models to start to recover some of that missing capability. And so large language models, obviously extremely powerful, have definitely brought language technology and machine learning to the forefront of not just the computer science community, but now pretty much it's been the tech topic of the year for 2 years going on now. And you know, obviously they're very powerful, but there are things that they're just not built well for. And there are some things that maybe a language model by itself might be able to eventually do. And then there's some things that really seem implausible that a language model without some augmentation would struggle to do. So the objectives for this course, first, we want to just show modern techniques for extending large language models to a wider range of speech and language tasks than just next token prediction and generation. We want to make sure that this is something for everyone. We're assuming pretty limited knowledge. This is targeting maybe the college freshman level. I'm sure you MIT students are very precocious, but we're not assuming that you have built your own, you know, massive language model or that you have huge amounts of ML experience, although I'm sure many of you do. And then there are going to be challenge questions at the end of every lecture that we'll give the answers to, or exercises that we'll give the answers to at the following lecture, which is how we did it last year, and that was very popular. Prerequisites, we want you to be excited about machine learning and speech. We assume some familiarity with the mathematical language machine learning, things like optimization theory, but we're not going to be necessarily getting too deep into like the math of ML, but some of the lectures might be more than others. So the course schedule, we have picked 4 themes for the next 4 weeks. And we will be doing kind of a call and response, where the first lecture each week will be focused on the science of that limitation and how either other algorithms or humans are good at that task. And then the second lecture will get into the mechanical details of how in 2024 you implement some of these things as augmentations of language models and recover some of that missing capability. So staff administration. So I don't know, Fulong, if you want to come up real quick. So this is Fulong. She's actually the person who put together this lecture series this year. She's a recent PhD graduate from MIT. Do you want to introduce yourself real quick?
Hi, everyone. My name is Fulong. I'm a linguistics PhD, recently graduated from MIT, and I recently joined the company to try to become an engineer. Please feel free to use me as a point of contact for any questions and concerns. And I hope I do as good a job as Grace, our virtual bot. Thanks.
Right. And Fulong will be giving a lecture the 4th week on language. So course support, we have a mail list, IAP@gridspace.com. Some of you have already been emailing it, which is great. We're going to be posting these videos on our YouTube like we did last year. If you are in this meeting, it's great if you can sign a release so that we can use your questions or video on our YouTube. And remote versus in California, I don't think we have anyone in person this year, but you guys, if anyone is in Southern California and you want to come to these lectures in person, you are welcome to, as long as you're signed up for the class. All right, so structure, I already covered this, 8 lectures over 4 units, call and response. If anyone does any projects that you want to show, like we did last year, we'd always be happy to give you time to show some of your projects in terms of extending LLMs. All right, let's get into the material. So 4 easy tasks that a human being can do that an LLM can't do. But we're going to start with a story. Has anyone ever heard the fable of the fisherman and the genie from Arabian Nights? No? Okay, great. I didn't make it up, but it doesn't really matter if I did because it's a fable. So the story talks about a fisherman who is casting out nets, bringing in junk, and then he ends up bringing in a ceramic pot with the seal of Solomon on it. And he's excited because he thinks that he's going to be able to sell this for a lot of money. But then when he removes the top to see what's inside, a powerful genie comes out. And the genie has nearly infinite power, but has been trapped in this bottle for hundreds of years. And the genie is furious. He says for the first 100 years, he had told himself, whoever freed him, he would give them infinite wealth. After 100 years, he softened a little bit, and he's like, okay, well, if someone frees me, I will give them some wealth. But then another 100 years passed, and he's like, okay, fine. If someone frees me, I will give them 3 wishes. But by 400 years, he was so furious, he decided that when he was eventually released from the bottle and could bring his full wrath on whoever let him free, that he would only let them choose how he killed them. And this omnipotent being released upon this poor fisherman tells the fisherman that he can choose the way that he dies. And the fisherman, who's very clever, but not, a super powerful being, outsmarts the genie and tells the genie, man, how did you fit in that little bottle? And the genie's like, oh, it's very easy. I can shapeshift. And he goes back in the bottle. Then he pops the top back on. And he actually gets the better. The genie threatens to throw the genie back in the ocean. And the genie relents that he'll actually grant him a wish if he frees him again, which he does. The LLM of 2024 is like the genie. It's a super powerful system. And we maybe, in some ways, are not as powerful as it, just like we aren't with a lot of other machine learning algorithms or algorithms in general. But it has its weaknesses, and its weaknesses all come down to common sense. And so what we want to do is put the genie back in the bottle and contain it and use it so that it's able to solve tasks that are useful for us. That's the goal of this course, is to put the genie back in the bottle. We know it's very powerful, but we also know that common sense is not its strong suit. What is common sense? I'm going to name 4 things that any of us can do without much thinking about it. First is maybe play a game like chess. It's from the 7th Seal. Second thing maybe we could do is do some research or look up information and then produce some sort of coherent result from it. This is from All the President's Men. We can look at a painting or a piece of art and describe how it makes us feel and talk about it and examine it. This is from Ferris Bueller's Day Off. Or maybe we could prove a mathematical theorem, which Cole will be covering in the 3rd week or the 4th week. This is from A Beautiful Mind. The first shows planning, which is what I'm going to be talking about. The second, memory. The third, perception. And the fourth, language and symbolic reasoning. These are 4 things that we take for granted, not just as people, but also with computers in specialized contexts, right? So remember, language models are very powerful, but there are algorithms, some of which are very simple, some of which are 100 years old or older, that can sometimes do these things trivially. So it's not about getting computers necessarily to do these things. It's about trying to get general purpose AI that can do these things in the context of language, right? Which is a distinction that's subtle, but it's the crux upon which most of the remaining open problems in AI hangs, which is how do you build general purpose systems that in addition to natural language can solve general tasks that we all take for granted. All right, so we're going to start by talking about algorithms. So algorithms nowadays, we kind of take algorithms to be equivalent to like computer work. But algorithms, it's an ancient concept that goes back long before computers, like Arabian Nights. Originally, it's an Arabic word. So one example is long division, right? So we all learned this like 3rd grade, right? So this is something that's from WikiHow, by the way, where if you ask me 250 divided by 6, I might be able to come up with it in my head. You give me a sufficiently long and not a very long, multiplication or division problem, I'm not able to just in my phonological loop figure it out. I can't visualize it. I can't just figure it out in my head. Maybe you can, I can't. And so there's an algorithm on paper where we use the data to store and manipulate information to augment us as language-focused beings who might have an internal monologue, might have the ability to visualize things. And so this shows that even a person has to sometimes be augmented with tools to be able to execute algorithmic tasks. And computers are just an extension of this work that started with abacuses and paper, and then obviously progressed to like the differential engine and then eventually computers. So there's things like sorting algorithms, right? Which you all, if you haven't learned already, you'll learn in your first minute of computer science education, or tree search or graph search algorithms. You can start to learn that you can form data structures out of more primitive data structures that allow you to intelligently represent that data so that you can then execute increasingly clever algorithms on the well-stored and well-presented data. This is essentially the main thing that you do with computers is store data in clever ways and then operate on those data structures in other clever ways. You might also get into like numeric algorithms, so like matrix inversion in this case, or maybe numerical methods, or maybe you start learning about algorithms for geometric algorithms or for rendering. And there's all kinds of specialized algorithms, some of which are very special purpose and very good. And if algorithms are doing something that a person can do, like division, they can blow people out of the water and have been able to sometimes for over 50 years. And so the idea of computers being able to do things that people can also do better than people has been around since the word computer, which originally is short for human computer. Computer used to mean a person who did lots of arithmetic for research or for accountants. So here's an example of popular algorithms book, the famous CLRS algorithm book on the left, or numerical recipes on the right. These are compendiums of algorithms that we've been having computers do in specialized ways for years. And then obviously there's specialized subfields, machine learning being one of them. But the point I wanted to get down is many of the problems that a language model or maybe machine learning struggle to help us with isn't because language models are not very powerful, or the model, the algorithms like the transformer or gradient descent that were used to build that model are not powerful. It is just that they are not specialized. And that's why right now in the field of AI, for a fairly long time, a lot of the focus has been on building systems that are more general purpose, like a person is, rather than needing to have some sort of specialized expert do years of research to discover a special purpose algorithm that can perform optimally. But obviously, there's nothing keeping a computer software system from using another computer software system, which is where augmentation comes in. But first, I want to talk a little bit about what people do specifically in terms of imagination and planning, so we can learn a little bit more about really like what the target is, or the bare minimum target is for planning. So I'm going to start with a chess puzzle. This is today's chess puzzle, actually, on chess.com. Here, I've just solved it. So does anyone have a guess? It includes anyone in the chat if you want. What would be a good first move here? We're black, yeah. Anyone on the chat? Anyone know? Queen up to take the bishop. Perfect. That's right.
Really?
Yeah. All right. So then he responds by taking our knight with his bishop, his other bishop. So we could take that bishop, and so then it's an even trade. What would happen if I did that? Lose your queen. Yeah, he then takes with my queen, and now we're down a lot. So discovering Zug means basically doing an intermediate move, an intermezzo, where we do this, and then we take, and we win. We had to look a step ahead to figure out what to do. I literally just picked today's chess.com puzzle because this is like every game of chess you've ever played. That's what the game is all about, planning. And so that's something that we take for granted. But whether you're sorry, let me share my screen again. Thanks, Natalie. Yeah, whether you're driving and you need to predict what would happen if you turned right or if you slammed on the brakes, or if you are walking down the street and you need to think ahead about like whether to step on that puddle, what would happen if you stepped on the puddle, how can you go around it? Planning is a fundamental part of general cognition, and it's something that computers have been pretty good at for a long time, especially through like graph search algorithms and other forms of planning, including chess playing algorithms. In daily life, like often you have to use what we call common sense, which is a combination of knowledge, the ability to make predictions, and the ability to incorporate past experiences. In this case, the first 5 or 6 times I touched the stove, I got burned, but by the 10th or 15th time, I learned not to touch it. And so you have to be able to visualize sometimes one or multiple actions ahead as part of your planning process. If you are a military general and you need to write down the orders for your troops or for your reports, you might have to first form a very complex strategy exploring many scenarios to their length before you can put a word to paper. Right? That's what strategic planning is all about, is thinking through, well, if I do this, then this might happen, or this might happen, maybe with different probabilities, long before you actually put a word to paper. If I tell an LLM to come up with a military strategy, it will make something that sounds like a military strategy. It might be something that is self-consistent, especially forward-looking from the start. But especially autoregressive token generation, where you just predict one word at a time, there is no detailed planning process. It just starts writing, which we've all done that, right? Sometimes instinctively respond to something and then realize we just didn't really think about what we were saying. That's essentially what autoregressive language model generation does. Autoregressive just means you only use what you've generated so far to generate another word, and then use all of that to generate your next word. And so it'd be very hard to put together some sort of strategic plan, although we'll revisit this in a second. This is from the notes of Dostoevsky when he was writing Brothers Karamazov. He had hundreds of pages of very, very detailed notes before he put a word to paper. Now, not every novelist writes this way, like Stephen King writes without very much planning. But if you wanted an LLM to generate a novel of text, there's nothing keeping it from generating that amount of text. In fact, any language model can generate text pretty much indefinitely. It's not about length. It's about coherence and planning. You're not going to get a language model to generate Brothers Karamazov. Well, you probably can get it to generate exactly Brothers Karamazov, but you're probably not going to get it to generate another Brothers Karamazov. But maybe someday. But like you can see here, for just writing a book, which is literally language generation, planning is pretty critical to being able to do something good. And which is why in the language model context, planning is a central focus right now. I mentioned this earlier, but this is an example of just an algorithm for chess that doesn't require machine learning. It is this min-max with alpha-beta pruning has been used for many years to first solve like tic-tac-toe and checkers, and then in the 90s chess. And so this is an example where a computer doing a relatively simple algorithm with no learning element is able to perform its superhuman abilities without any use of machine learning at all, certainly without a language model. And so what we see is that traditional algorithms and people both really can perform pretty well at these tasks that a language model might struggle with. And so the goal is not to just get a computer to do this now, it's to get a general purpose machine where we can instruct it in natural language to do it well. So before we look at augmenting LLMs with search, we're going to look at kind of the other direction. We're going to look at DNN augmented search and games. So one of the first maybe landmark applications of deep learning in the last 10 years was DeepMind's work with Go and just general game playing. So this is from the papers of the AlphaGo and then AlphaZero, where the idea was at the time top Go playing algorithms and also a lot of top chess engines use the form of tree search called Monte Carlo tree search, where you aren't necessarily searching every single path or just pruning it, but you're actually doing something stochastic, or the Monte Carlo algorithm, where you're picking random nodes weighted maybe by the likelihood of being good, and then you're exploring random nodes from there and from there and from there, and eventually then you evaluate the leafs, and then you compute a score for that path and then the path above it, and then that helps you continue to figure out which nodes to expand and which direction to go. And this is already a very powerful algorithm that was already starting to get good results in Go, which had been pretty impenetrable to AI for a long time because of this large search space. There's 361 points in a Go board compared to the typical number of moves in chess is somewhere around 30. And so, 30 to the n, it grows a lot slower than 391 to the n. And so the idea was, initially, it was a little more complicated, but by AlphaZero, the idea is that you just augment with one specialized convnet it was really good at doing the pattern recognition aspect of Go or chess. They actually look at several games in the paper, and is able to, given a snapshot of a board, figure out who's winning and by how much, basically predict how the game's going to end. And that allowed Monte Carlo tree search at its leaves to be a lot more intelligent and also be more intelligent about selecting directions to pursue. And so by augmenting a traditional search algorithm with a neural network, you were able to perform substantially better. And if you look at Stockfish, the best chess engine in the world by rating, currently, they were actually fairly resistant to incorporating neural networks at all for a very long time. They instead focus on highly optimizing Monte Carlo tree search, which got it very, very good. And a lot of what their focus was just essentially just systems programming and how you represent the board using something called a bit board and how you very efficiently store explored states, just kind of typical old computer science. But eventually, they figured out that they could train a highly compact neural network for evaluation and get things better. And there's other very competitive chess engines that much more heavily rely on neural networks. And so by augmenting your traditional algorithm with just a little bit of a neural system, you're able to, or machine learning system in general, you sometimes can get much better results. This is a figure from Cicero, which was a meta paper from a year ago. Has anyone ever played the game Diplomacy or read the paper of Cicero, one of the two? Which one? You played the game? I actually hate the game. It stresses me out. I don't like Risk either. When I was in high school, I used to play Diplomacy, but the Diplomacy is like Risk, but with a lot more talking. So if you haven't played Risk, you have a map of the world and you're trying to conquer it. And in Diplomacy, there's this period where you can kind of talk to the other players and convince them to form alliances. And so it has this very large amount of planning, like Risk, but augmented with all these other language tasks where you have to not just communicate with other people, but also plan out the result of your dialogues with people. And so Cicero was a really cool paper in 2022 where this team at Meta was able to augment a traditional game playing algorithm, a special purpose game playing algorithm for Diplomacy, with a large language model to engage in dialogues with other players, and it was able to outperform other players. But there's no way you're going to do this with Monte Carlo tree search, because at the fringes you need to have dialogues, which is something that a language model is much better equipped for doing than something that you would do just with a very small discrete state space like a chess playing algorithm. So these are examples of augmenting, traditional computer science algorithms with, like tree search in both of these cases, with language models. But there's also ways that you can, with very, very simple algorithms on your prompting process, begin to get much better results out of language models themselves. And so some of these things you may have already heard of or even done. But recursive prompting is an umbrella term for some sort of algorithm, typically a very simple algorithm, where you are prompting or reprompting a language model multiple times to try to get better results out of it. So the simplest one is chain of thought reasoning, which was published in 2022. And the idea is that you force the language model through the prompting process or reprompting process to show intermediate work, so that it has access to its intermediate work as a very simple linear form of planning. This idea was extended in libraries like LangChain to also include hitting intermediate tools. But the idea is that you very linearly are performing intermediate results as scratch work and then proceeding from there. And a lot of human hand algorithms, like the long division we saw earlier, kind of resemble this process. And so they have examples here where a math problem is broken down into pieces by necessity by the language model, and it's able to show its work and get the correct answer, and in this case, an arithmetic question. Arithmetic is something that generally language models are not well built for, without some form of augmentation, of which there's many different approaches, which we'll cover in other parts of the class. But in this case, by using chain of thought, you force the language model to show intermediate work and then take steps, which already, in terms of catching up to human cognition, is a fairly big leap. And the algorithm that we're putting on top of the language model is essentially just dividing its generations into intermediate structured parts. We're essentially guiding it through a process by splitting a task into smaller subtasks. Now, that doesn't always necessarily generalize well. So maybe you can, in a really hand-designed way, design a chain of thought reasoning process for a specific dialogue system task or a specific language processing task. But generalizing chain of thought reasoning isn't as easy as maybe using it as a specialized tool, but as a tool that was discovered pretty early on as language models have gotten bigger, as a way to extend their capabilities without building any new model. An extension to that is something like Tree of Thought, which was published late last year. I think this is a meta paper. The idea is the same, except you're exploring a tree of states. So you're allowing it to actually start to do a little bit of what we saw in other tree search algorithms more traditionally, which is, okay, I could say one of these several things and then, or generate one of these several things. And I think Tree of Thought, they actually show, explores multiple different drafts or concepts, and then keeps continuing to follow paths that seem promising, quite a bit like the tree search algorithm that you might see in a chess playing algorithm. This is even more powerful, the idea that you might search a tree to augment your language model, which is going to be the idea that we're going to build on beyond just prompting. By the way, this is a pretty good survey paper from early last year, Augmented Language Models, a survey. A lot of the material we'll cover in the class, not just for planning, is surveyed pretty well in this piece. But this is another example of how you can essentially force chain of thought to provide some form of working memory for solving multi-step problems. Before I move on to the next section, are there any questions on what I covered so far? I'm about maybe halfway through the material or 2/3 through the material. Anyone up here? Don't be bashful. Anyone in here have a question?
You say what tree of thought?
Yeah, so it's similar to chain of thought, but the idea is that you force the system to form sub-pieces with multiple alternatives, and then continue the generation process from favored paths and just continue that process. But it's like pretty similar to any other kind of like greedy tree search. But you need some sort of heuristic for what's a good generation, which, you know, you essentially are doing that in a hard-coded way with chain of thought, where you're saying like, do this, or, oh, does Tree of Thought use an LLM to judge the goodness of the response? I think it does. Yeah, I think it's using an LLM for almost everything. And that's what you see with a lot of these recursive generation algorithms, is that the LLM is doing almost everything, and the algorithm is something really simple, but you are splitting a task into subtasks so that everything isn't just one autoregressive generation. You're forcing it to stop, pause for a second, evaluate what it's done, and then make decisions in the case of Tree of Thought. based on several generations. But and to be honest, Cole, I'm kind of presenting tree of thoughts as an example of the types of stuff you can do. The truth is, like, there's really no limit to the things you can cook up in terms of like other generation schemes where you're trying to get the system to have a little more truthfulness, to be a little bit better at planning. Although I do think that just these prompting schemes leave a lot of power on the table, which we'll get to in a minute. Evaluated together with like the same. I haven't read the paper in a long time, but I think they evaluate all the alternatives against each other and then pick the best. But I actually can't remember. I'm guessing Cole is reading the paper right now, so maybe he knows. Any other questions, guys? Thanks. Was it Michael who asked the question? Thank you. All right. So let's pull all these kind of ideas together. So we've seen how you can reprompt a language model and break pieces into sub-pieces all the way up through some sort of tree search process. We've seen how you can augment tree search processes with machine learning models. And we've seen how planning is traditionally done in algorithms and people. And so if we bring that together, we can get to that concept of search augmented language models. This is actually from a paper that's more focused on information retrieval, which we'll be covering next week, I think. But I like how it shows that at the boundary, language models they're very powerful. They're the genie in the bottle, right? They're this omnipotent genie in a bottle. But at the fringes, they have these limitations. And what it's showing is capabilities, memory, and knowledge. Now, planning, you could kind of look at it as all three, especially memory and capability. Planning allows you to, like you might do on a scratch pad, work out various solutions, exploiting that scratch pad to explore ideas, like you might see in like the Tree of Thought paper. But it's also extending your capabilities, where you take a language model which is not really designed for like search or other traditional algorithms, and you're giving it access to basically a computer, right? So this, I think, shows that pretty well, and it also provides a pretty good foundation for a lot of the other stuff we'll be talking about in this class, which is LLMs have these boundaries that we have to augment to transcend. And you can augment some, or you can transcend some of these limitations by just making your language models bigger and bigger, right? So like as context windows get bigger, some of the memory limitations become less significant, and we'll be covering that I think in Nick and Lokman's lectures. Traditional reinforcement learning, where you are pulling information from the environment and then picking actions, is a really simple form of sometimes learned tree search, where you might have like a Q matrix where you're learning how to map environment states and observations onto a most favorite action. And in general, this is, again, something you might typically learn in a first AI course, or maybe in a reinforcement learning course, when you're talking about how can you use AI agents to plan. In fact, planning is the main thing that reinforcement learning does. And so it's not that even planning is new to the field of AI, and it has been extended to neural methods too, originally with the deep Q learning that was used in the DeepMind Atari paper a decade ago. And the idea was that, okay, we already have a pretty good planning algorithm in traditional AI, and we also have these more and more powerful neural networks that are capable of like perceiving the environment. In their case, they had, I think, like a CompNet that perceived the state of like, an Atari game, and then is able to pick actions from the small number of actions that the Atari controller allows. But this idea of augmenting planning algorithms with neural networks, like we also saw with DeepMind's AlphaZero paper, is not that new. And so the real question is, how can we get this into the language modeling context? Cicero already shows one example, but one very special purpose example that's not going to generalize to like general game playing or general task solving. Another example of planning in traditional AI is A*. So A star is a form of greedy search, or breadth first search, depending on how you look at it, where you're not necessarily finding the best path, but you're finding a fairly good path using a heuristic. A heuristic being a shortcut rule of thumb for which path is the best. And so you explore multiple paths and then rank them by basically performance against this heuristic. So so we see different ways where search and planning shows up in traditional AI, and also ways where, again, we've extended it with neural algorithms primarily for perception or for acting essentially as a heuristic. So now the only remaining piece is really how do we do the same thing with language models? And we see this all the time when we generate language. So like this is like, I don't know if anyone's ever seen this, but this is like a paper where you've done editing markup, or maybe track changes in a Google Doc. And when someone is writing multiple drafts of a document, you are essentially doing what we want to augment a language model to be able to do, which is generate something somewhat with some degree of planning and review what you've generated, and then either point-wise plan changes that you want to make or generate a new draft from scratch. And this form of planning is essentially what we really want to do. And you kind of see like the beginnings of this in things like chain of thought and the other recursive prompting, but that's a really structured special purpose way to do it. And so we want a generation process where we're exploring different generations and then picking generation paths that seem plausible against some sort of good heuristic. Another example is if you need to use your imagination and explore many scenarios, it's very useful to be able to not just plan out what you say, but also plan out the impacts of your actions. Again, you see this in reinforcement and DeepQN all the time. You just don't typically see planning for what the impact of your generation might be on the world as part of that generation process, where you're probably just doing like, greedy autoregressive, text generation, right? Where you're not really doing very much planning about, as an agent, hey, what should I say to generate the best long-term outcome? All you're trying to do is maximize the likelihood that you generate text that resembles text in your training data, which is a task that really doesn't require that much planning beyond what a transformer is already capable of doing. All right, so that's all the material I had. What I wanted to do was show that we kind of have all the tools to do what we want to achieve, which is starting to incorporate graph search into language model planning in a way that's more sophisticated than maybe just the tree of thought paper, but we're actually starting to do something that looks like A star or deep reinforcement learning, where you are actually, through either a traditional tree search or some other process, figuring out as an agent what is going to be the impact of the generation that I generate multiple steps ahead. That's what we're trying to motivate here, which is that's how people plan, and that's how other algorithms plan. And that's also a task that we've kind of solved in reverse with things like AlphaZero and Cicero and with deep reinforcement learning. So we have all the tools we need to start to explore ways of extending language model text generation to incorporate planning. And there are a lot of people working on this problem. This is not the fact that this is if not the problem in all of AI right now is not super controversial. And that this is generally the direction that we all need to move is also not really that controversial. It's the how that we make this work that is still at the bleeding edge and is basically at the forefront of everyone's work. So I'm going to leave that to Wonkyum for Thursday. So I have 3 exercises. So the idea is that you should work on this either if you're watching the video or whatever, and we'll show the answers next time. These are kind of pretty broad questions. So the first is just hallucinations. So generating something that seems true but is not true, but is likely that might have occurred in your data set is a really common problem with LLM generations. So the question is just what are strategies, including ones I mentioned, but also there's others, for maximizing truthfulness in model outputs? The second question is how might you align an LLM to write or to play a novel abstract strategy game using only the description of the rules. So this is not something that really anyone has done well, but the idea is like you give it the manual for a game, and it doesn't just play it; it plays it well. So it plays it like Stockfish plays chess. So how maybe in broad strokes, how might that be done someday by someone? And again, general game playing is a very big grail, maybe one of the grails in AI. Third question is Stockfish, which I already mentioned. Currently the most powerful chess engine by rating. So I want you to do some research, maybe even look at some of Stockfish's code, and based on your own research, try to put numbers on how much of the immense power of this system can be attributed to machine learning versus non-machine learning algorithms, notably tree search, but also other very, very smart optimizations like bitboards. Cool. So here are the references. A lot of these I actually pointed out in the lecture, but these are a pretty good outline of where things currently are in terms of planning on augmented LLMs and things that are approaching the problem from other directions. Does anyone have any questions? All right. Well, so rewinding. Here's the schedule again. So on Thursday, Wonkyun is going to be covering tools for LLM planning. It'll also have the answers to these exercises. And then next week, we will start talking about memory. So thanks, everyone. I really appreciate it. Sorry we started late, but we'll start on time on Thursday. And appreciate you guys watching.
Hello, thank you for calling Gridspace's YouTube channel. Did you make sure they liked the video and smash that subscribe button?
Yes, I did.
And ask them to leave any questions or thoughts in the comments. It helps me a ton. Thank you for watching, and if you'd like to talk to me yourself, go to gridspace.com and click on any one of our demos. Thank you, and talk to you soon.
Thank you, Grace.